Now let's prove the spectral theorem for self-adjoint operators. And if I apply this to real symmetric matrix, it will give me the conclusion for real symmetric matrices. I can apply the theorem about self-adjoint operators to the linear operator which are induced from Hermitian matrix, and it will give me the spectral theorem for Hermitian matrices. Yeah. So spectral theorem for self-adjoint operators. So take V to be a finite dimensional inner product space over a field of scalars F, and let T from V to be a self-adjoint linear operator. Yeah, so keep at the back of your mind that self-adjoint operators are nothing but the linear transformations which are induced from real symmetric matrices acting on Rn, or Hermitian matrices which are acting on Cn. Yeah, just think of these things. But we are proving the theorem for abstract self-adjoint linear operator, because my vector space, inner product space, may not consist of ordinary vectors. It may consist of functions. And linear operator could be differentiation operator. It could be integration operator. Yeah, my vector space may consist of matrices. Yeah, it could be the vector space of symmetric matrices or Hermitian matrices or all n by n matrices. Then we have self-adjoint operators. Yeah, and you will see self-adjoint operators coming out of differential equations in the next part of the course, 108. Okay, and so it's good to prove a theorem for self-adjoint linear operator acting on a finite dimensional inner product space, and then it will apply to many different situations. Okay, so I have a self-adjoint operator on a finite dimensional inner product space. Then there exists an orthonormal basis of V consisting of eigenvectors of T. Yeah, so the vector space is V. We want to construct a nice basis. Nice bases are just like the basis of Cartesian space. The Euclidean space has nice bases I, J, K, which are unit vectors and mutually perpendicular. Analog of these kinds of bases are the orthonormal bases, in which any two vectors are mutually perpendicular and they have unit length. Yeah, so it is nice to have a basis like this, but not just arbitrary basis. This basis consists of eigenvectors of T. And I have explained to you that if the basis consists of eigenvectors of a linear transformation, then the matrix of T with respect to that basis is a diagonal matrix. So it is the best matrix that you can expect with respect to a given basis. Yeah, so we have finite dimensional inner product space over a given field of scalars. It could be real or it could be complex, and I have a self-adjoint linear operator. Then there is a orthonormal basis of the vector space consisting of eigenvectors of T. Yeah, so we are going to apply this by induction on the dimension of the vector space. Yeah, suppose the dimension of the vector space is 1. Then it has a basis consisting of a single non-zero vector. Yeah, a single non-zero vector, I can divide by its length and get a vector of unit length. And then the vector space will be the linear span of that vector. It consists of all the scalar multiples of this unit vector. Okay, and if I apply T on this vector V, this is the vector which is desired. It is an orthonormal basis. A basis consisting of one single vector of unit length is also orthonormal basis, because there is no other vector with respect to which we have to check the perpendicular relation. Yeah, a single unit vector is also orthonormal basis. Yeah, but let us see that it is an eigenvector, because the vector space is one dimensional. If I operate T on V, I will get a scalar multiple of V. Yeah, that's how all the vectors in V look like. They are scalar multiples of V. So TV is BV, and V is a non-zero vector, and therefore V is eigenvector and B is the corresponding eigenvalue. Yeah, right. But we have seen that Hermitian matrices have only real eigenvalues. Yeah, so there exists a lambda in R and a unit vector V, so that TV equal to lambda V. Okay, right. So I'm now proving the theorem for higher dimensional case. Dimension is 1. We are done. The given basis consisting of this unit vector, that is a eigenvector with eigenvalue B. So we are done. We wanted to prove that any self-adjoint operator has a basis consisting of eigenvectors. Yeah. So here we have a basis consisting of eigenvectors in one-dimensional case. Now assume that dimension is at least 2. Yeah. So when I take the matrix of T, it is a symmetric matrix or Hermitian matrix, but Hermitian matrices have only real eigenvalues. This I have proved in the last class. Yeah. So there is a real number lambda, and there is a unit vector, so that TV equal to lambda v. Yeah. Right. So to find eigenvectors and eigenvalues of a linear operator, we can take any basis, construct the matrix, and find out the eigenvalues and eigenvectors. Those are the eigenvalues and eigenvectors of T. Okay. So we know that if I take a self-adjoint operator, then its eigenvalues are only real. So I pick that eigenvalue and corresponding eigenvectors, so that TV equal to lambda v. So I have one vector to begin with, but I want to now extend this this one single unit vector to a basis which is orthonormal basis of v. Okay. Yeah, and we want to apply induction. So by induction, whenever I have a linear operator which is acting on an inner product space of smaller dimension than D, then the theorem says that we have a orthonormal basis of eigenvectors. That is the induction hypothesis. Okay. So I have one vector in my vector space, of dimension D, which is at least 2. I have one vector v, so that its TV is in the same direction. TV is equal to lambda v. Okay. Now I am looking for a trick to apply induction hypothesis. Yeah, induction hypothesis can be applied to inner product spaces of dimension less than D and linear operators which are self-adjoint, acting on those. Okay. So I have this one vector v. What I do is I take a plane which is perpendicular to this. Okay. I take a plane which is perpendicular. What is the analog of perpendicular plane? Well, it is the space of all vectors which are perpendicular to v. Okay. That is in dimension 3, this becomes a plane which is perpendicular to v. But in arbitrary inner product space, this is the space which is perpendicular to the vector v. All right. Now let's observe that dimension of W is actually D minus 1. Okay. So V is my big inner product space, and I took W, which is the space which is perpendicular to a given unit vector V. Okay. And I have this linear operator T acting on V, which is self-adjoint. Okay. Now let us prove that this linear operator is actually mapping vectors in W to vectors in W. If T is self-adjoint, then it is this property that for any two vectors, UTV is same as TUV for any pair of vectors. So the same property will hold if I take pair of vectors in W also. So this T is automatically self-adjoint. What is not clear is that T takes vectors in W and produces vectors in W. So if we assume this, then T becomes a self-adjoint linear operator on a subspace of dimension D minus 1. So by induction, I have eigenvectors of T which are contained inside W. Yeah. By induction, there exists W1, W2, WD minus 1, which are eigenvectors of T. Yeah. And there will be real eigenvalues, lambda I, Wi. Okay. So these vectors are inside W. They're all inside W. Okay. And this vector V was perpendicular to W. It is perpendicular to every vector in W. So V will be perpendicular to W1, W2, WD minus 1, and V has. So we know that when I take a set of vectors which are mutually perpendicular, then they are linearly independent. So I attach this V to W1, W2, WD minus 1. I have a set of D vectors which are mutually perpendicular. They have unit length, and therefore I would have constructed a basis of eigenvectors of T for the whole space. Okay, so the only thing we have to prove is that when I restrict T to this subspace W, the T will map vectors in W to W. But to prove that T maps vectors in W to W, I go back to definition of W. Okay, so pick a vector in W, which means this vector is perpendicular to V, and I apply T. I have to show that the image is inside W. I have to show that the image of the vector in W under the action of T is again perpendicular to V. Okay, so perpendicularity relation is preserved by if a vector was perpendicular to V to begin with, and then I apply T to the same vector and I get the image, that image is again perpendicular to V. That's what we have to prove. Okay, so let us look at that. So we want to show that if W belongs to W, then TW is also in W, and T is self-adjoint, so we can apply. So to prove that TW is in W, I have to check whether it is perpendicular to V. So take the inner product of TW with V, but because of self-adjoint property, this is WTV. Yeah, but WTV, V is eigenvector of T. So TV is lambda V, and this lambda is real. So it comes out anyway. So lambda times W comma V, that is 0, because W and V were perpendicular. Yeah. So therefore, TW is perpendicular to V. So if V is perpendicular to W, then TW is also perpendicular to V. So TW belongs to V. So I have proved that when I restrict T, this linear map from V to V to W, I get a self-adjoint linear operator on W. W is, now we have to see that W is D minus 1 dimensional. Okay, W is D minus 1 dimension. Now this we have seen this before. Let me recall why the dimension of W is D minus 1. Okay, dimension of W is equal to D minus 1. Okay, so W consists of all vectors, so that all vectors U, so that U is perpendicular to V. V is fixed unit vector, and I am looking at all vectors which are perpendicular to V. Okay, so I want to prove that this is dimension D minus 1. Okay, so let us define a map from V to F. It takes a vector U and maps it to its inner product with V. Okay, let's consider this map F. Okay, so F is a linear transformation. F is a linear map. Why? Because F of U plus U prime is equal to U V. Wait a minute. I need to, because of conjugate linearity, I need to change this. This is equal to V U, inner product of V with U. Okay, so F of U plus U prime, F of U plus U prime. Yeah, F of U plus U prime is equal to V U plus U prime, and that is equal to V U plus V U prime, because it is bilinear. The inner product is bilinear, and F of alpha U is equal to V alpha U, and these scalars come out as they are. Okay, so therefore F is linear. It's a linear transformation from V to F. Okay, now what is F of V? F of V is inner product of V with V, and that is equal to 1, because V is a unit vector. Okay, and this F is one-dimensional vector space, and its image of F is non-zero scalar, which is 1, and therefore F is on 2. Okay, so the rank of F is the dimension of this image, but the image is whole of F, so rank of F is 1. Right? But the rank nullity theorem for linear transformation says the rank of F plus nullity of F is equal to dimension of V. Dimension of V is equal to D, but rank of F is 1. So nullity of F is D minus 1. Nullity of F. What is nullity of F? Nullity of F is all vectors which are mapped to 0. Okay, so all vectors U which are mapped to 0. But this means that inner product of V with U is 0. And these are precisely the vectors which are perpendicular to V, and that is the subspace W, and therefore the null space of F is W. W is the null space of F. And by rank nullity theorem, its dimension is D minus 1. And there, so we can apply induction hypothesis. And so there is the orthonormal basis of W consisting of eigenvectors, and then you put V along with this basis, V union B, that's the required orthonormal basis of V of eigenvectors. So I have proved that if I have a self-adjoint operator acting on a finite dimensional inner product space, then it has a orthonormal basis of eigenvectors. Okay, yeah. So let us understand the eigenspaces a little bit more, and let us prove that the eigenspaces of self-adjoint matrices are mutually perpendicular. So there are many eigenvalues of the given self-adjoint operator, and for every eigenvalue there is a eigenspace. Okay, there is an eigenspace, and this theorem says that the eigenspaces are going to be mutually perpendicular. Okay, so suppose I have a self-adjoint operator on finite dimensional inner product space. Suppose U and V are eigenvectors with distinct eigenvalues. Yeah, so lambda give rise to the eigenspace E lambda. E lambda consists of all vectors, so that TV is equal to lambda V. That is the eigenspace of this eigenvalue. Okay, and similarly mu gives rise to the eigenspace E mu, and we have seen before that E lambda intersection E mu is actually 0 vector. Okay, it is 0 vector, but we are proving that they are actually perpendicular, not just they are intersecting in 0 vector like two lines passing through origin. Okay, if they are distinct lines, they will intersect only in the 0 vector. Okay, but if I have two planes which are passing through origin, yeah, in 3-dimensional space, they will intersect. If they are distinct planes, they will intersect in a line. But the eigenspaces are always intersecting in the 0 vector. There is no common vector between two distinct eigenspaces. Okay, but here we want to prove that if my linear operator is self-adjoint, then the eigenspaces are actually any vector in EW is going to be perpendicular to any other vector in E mu. Okay, so let us prove that eigenvectors in the eigenspace of lambda and eigenvector in the eigenspace of mu, they are mutually perpendicular. Okay, yeah. So let us look at let's use the self-adjoint property of T to show that inner product of U with V is 0. So take inner product of U with V, multiply by lambda minus mu. This is non-zero. Lambda is different from mu, so I have a non-zero. I have a number here, and this is going to be 0 if and only if U inner product with V is 0. Okay, but this is same as lambda U V minus U mu V, because lambda and mu are real numbers. They are real numbers. If they were complex, I wouldn't have been able to do this. I can just push mu here. Okay, this is same as lambda U inner product with V minus inner product of U with mu V. But this is equal to lambda U is TU and mu V is TV, because U is eigenvector corresponding to eigenvalue lambda and V is eigenvector corresponding to eigenvalue mu. So I have TU inner product with V and inner product of U with TV, but T is self-adjoint. So these two numbers are equal. So this is 0. Okay. So this non-zero scalar multiple of this scalar is 0. So this scalar has to be 0. Yeah. So this is done. So any two eigenvectors corresponding to distinct eigenvalues are perpendicular, provided the linear operator is self-adjoint. Yeah. So since the eigenspaces intersect in 0 and any two vectors, one coming from E lambda, another coming from E mu, or they are perpendicular, the vector space, yeah, if I add these two subspaces W1 plus and W2, which are eigenspaces, their intersection is 0, then the vector space, we say it is a direct sum. Yeah. So if I add two vector spaces and make a big vector space, and if these two vector spaces are intersecting only in 0 vector, we say that the vector space is a direct sum of these two subspaces. Yeah. So take a self-adjoint linear operator acting on finite dimensional linear product space and list the distinct eigenvalues. These are all real numbers. List all the distinct eigenvalues. Then the eigenspaces, yeah, the eigenspaces, they fill up the whole space, because self-adjoint operator, I have proved that it is diagonalizable. It has a basis of eigenvectors. So I can take, so this basis of eigenvectors, a few of them will come from V lambda 1, another few of them will come from V lambda 2, etc., etc. So the whole vector space is a sum of the eigenspaces, but the eigenspaces are mutually perpendicular. They intersect in only 0 vector. So therefore, by the formula for dimension of this sum as being sum of the dimensions, dimension of V is sum of the dimension of the eigenspaces, and the vector space is a direct sum of eigenspaces. Okay, yeah. So for a self-adjoint operator, my entire space splits into mutually perpendicular subspaces, which are eigenspaces. Okay,